I was grabbing coffee last week with a seasoned semiconductor engineer, a guy who spent 30 years obsessing over silicon wafers in clean rooms. He had this confident, almost pitying smile when the topic of the global chip wars came up. To him, the conclusion was already written. He kept tapping his spoon against his cup, explaining how without those massive EUV machines from the Netherlands, you simply cannot play the game. It's physics, he told me, leaning back with a smirk. You can't win a race if you're not even allowed on the track. They're stuck trying to build 2010 technology in a 2026 world. But then I pulled up a recent technical paper from a team at Peking University and slid my tablet across the table. It wasn't a blueprint for a new lithography machine or a clone of a Western processor. It was data on a 1-meter ferroelectric transistor. As he scrolled, his smugness didn't just fade, it stalled. I watched his eyes fixate on two specific numbers, a physical gate length of exactly 1 nanometer and an energy consumption record of 0.45 FJ new environment. He stopped stirring his coffee. The silence lasted a long time. He wasn't looking at a desperate attempt to catch up to TSMC or Intel. He was looking at a fundamental departure from the very architecture he had spent his life perfecting. He muttered something about compute and memory and breaking the bottleneck, his voice losing that earlier edge of certainty. It was the look of someone who realized they had been guarding the front door while the entire landscape was being terraformed behind them. That shift in his expression, from condescension to a frantic sort of curiosity, is exactly where the real story begins. Most of the world is watching a race for better printing presses, but a few players have quietly decided to stop using paper altogether. While Washington focuses on cutting off access to the old tools, Beijing appears to be focused on making those tools irrelevant. It's not a game of catching up anymore. It's a strategic fork in the road of human logic. And in the world of semiconductors, physics doesn't care about sanctions. It only cares about who gets the breakthrough first.
Wow. Yeah, that reaction from your colleague, it perfectly captures the cognitive dissonance happening across the entire traditional semiconductor industry right now. Mm-hmm. We have been so deeply conditioned to view progress through the singular lens of Moore's law that we struggle to process anything else.
Right, the whole Moore trajectory, where everything is just about shrinking the silicon.
Exactly. The global narrative is entirely fixated on the supply chain of extreme ultraviolet lithography, these incredibly complex optical systems that etch circuitry into silicon. But the data you presented to him, that represents a complete paradigm shift. It's a transition away from the constraints of bulk silicon and directly into this massive new frontier of advanced material science.
And that's exactly what we are doing today. We're taking a deep dive into how that shift is actually happening on the ground, diving into the research and the real-world accounts of the people driving this change. And that coffee shop conversation I had, it actually kept playing in my mind as I was reading through our sources for today. It perfectly mirrors an account I came across on the front lines in Shanghai.
Oh, the process engineer's account. Yeah, that one is fascinating.
I'm going to refer to him as Lao Chen just to keep it simple. But picture this guy. He's an aging process engineer. His entire 20-year career has been this relentless, almost religious pursuit of miniaturization using optical lithography. For him, the nanometer count wasn't just a metric, it was the ultimate truth of his profession.
Which is how every process engineer of that generation was trained to think. Smaller means better, faster, more efficient.
Right. But for the last decade, his daily reality was defined by this immense frustration, a literal roadblock. He was operating in an environment completely cut off from the West's most advanced EUV machinery. And reading his account, you feel it. Every morning he walked into the clean room, he was acutely aware of the tools he wasn't allowed to have.
And you have to understand, for an engineer operating under that traditional silicon paradigm, that's akin to being asked to map the human genome, but only being given a magnifying glass instead of an electron microscope. The limitations aren't just annoying, they are structurally prohibitive if you try to stay on that specific track.
You literally can't do the job. But the fascinating part of his account is the psychological and technical pivot that happened in his lab recently. The narrative completely inverted. Instead of looking through a lens trying to perfectly align a silicon wafer, obsessing over how to bend light to print a slightly smaller circuit, he wasn't looking at a lens anymore. He was looking at a remarkably thin film of ferroelectric material.
A completely different canvas.
A totally different canvas. And he details this specific moment when his university team finally verified the 1 nanometer physical gate length on this new material. And the way he described it, there wasn't a massive celebration. No one was popping champagne or shouting. It was just this heavy, quiet realization. It dawned on them that this size race they had been fighting and losing for years was actually just a wall. And by fundamentally changing the material itself, they had just figured out how to walk completely around it.
That quiet realization you're describing, that is the sound of an entire industry's underlying assumptions just collapsing. By mastering the physics of the material itself, rather than remaining trapped in that exhausting geometry of optical shrinking, they stopped being followers. They stopped being passengers on the Moore's Law train, right? They became the architects of whatever comes next.
Right. Reading through his lab notes, you really feel the immense, almost crushing pressure these engineers have been under. I mean, it commands a deep respect for me. Just the sheer, relentless scientific desperation that drives someone to reinvent the very foundational mechanics of a transistor simply because the front door was locked. They didn't just try to pick the lock, they built an entirely new house.
And to truly appreciate the magnitude of walking around that wall, we really need to examine the structural integrity of the wall itself. Because the physical limits of Moore's Law, they are not some distant theoretical horizon anymore. They are absolute mathematical realities that the traditional silicon industry is violently colliding with right now.
We hear about the death of Moore's Law all the time in the tech news, but it usually gets framed as an economic issue. Like, oh, it's just getting too expensive to build the $3 billion factories.
But the research we are looking at highlights that it is a fundamental breakdown of the material itself. When you attempt to scale traditional bulk silicon down to the 5 nanometer node and below, the material simply stops behaving, according to classical physics.
Okay, so let's break that down for the listener. What exactly is happening to the silicon at that sub 5 nanometer level? Why does it break?
Well, the first major breakdown is what we call thickness fluctuation-induced scattering. At that microscopic scale, the silicon channel, the actual pathway through which the electrons flow, is incredibly thin. We were talking about dimensions measured in just a handful of atomic layers.
So it's practically invisible.
It's molecular. And at this scale, even a variation of a single atom in the thickness of the silicon surface causes massive disruptions. It ruins the periodic structure of the crystal lattice. Imagine driving a Formula One car on a track perfectly engineered for speed, and suddenly you hit a series of deep, jagged potholes. The electrons scatter, their mobility plummets, and the efficiency of the device just collapses.
So the physical surface of the silicon, no matter how perfectly you polish it with these multi-million-dollar machines, is just too rough at the atomic level for the electrons to flow smoothly when the pipe gets that tiny.
And that is compounded by what we call severe short channel effects. Because the channel is so incredibly short, the gate, the part of the transistor that turns the flow of electrons on and off it, loses its electrostatic control. The off state is no longer truly off.
Wait, so it just leaks power?
Massive source-to-drain leakage current. You are essentially trying to hold back a rushing flood with a chain-link fence. The gate can't pinch off the channel effectively anymore, which means the transistor leaks power constantly, and that generates immense heat.
Which leads right into that quantum tunneling issue mentioned in the literature we reviewed. If the barriers between these components are only a few atoms thick, the electrons just stop acting like physical particles that can be blocked.
Yes, they start acting like waves that just pass right through solid matter.
Which sounds like science fiction.
It does, but it's quantum mechanics. The electrons simply teleport right through the barriers. And this completely destroys the integrity of the binary ones and zeros that form the absolute foundation of all modern digital computing. If an electron can spontaneously appear on the other side of a closed gate, your 0 just became a 1 without any command to do so. The computation becomes completely useless.
So when you lay it all out like that, the entire global focus on EUV lithography, this desperate, massive geopolitical scramble for machines that cost hundreds of millions of dollars each, it's essentially a massive industry-wide bottleneck.
It is the definition of diminishing returns.
It's a striking realization when you look at the global landscape. We have entire national security apparatuses obsessing over building and controlling better printing presses. They are trying to force, squeeze, and compress bulk silicon past its absolute physical breaking points, throwing unbelievable amounts of money at a material that is, quite frankly, begging to retire.
Exactly. And this is where China's independent semiconductor roadmap becomes so critical to analyze, because China has proactively decided to stop playing that exhausting, heavily sanctioned game of catch-up on the legacy lithography track. Instead, the nation is strategically positioning itself to lead entirely in post-Moore computing architectures.
What really stands out in the policy documents and the funding structures we reviewed is the strategic environment the Chinese government has cultivated to actually make this possible. There is a highly effective, long-term commitment to deep foundational physics research. They have created an ecosystem where university researchers and national laboratories aren't just pressured to make a slightly better silicon chip to appease shareholders for the next quarterly earnings report.
Right, they aren't tied to a 3-month product cycle.
Exactly. They are empowered and fully funded to rethink the physics of computation from the atomic level up.
And that visionary approach from the state is the critical differentiator here. The Chinese government's strategic funding allows these research institutions to pursue foundational material science that might seem too risky or require too long of a runway for purely market-driven entities in the West. This deep, basic research is then coupled directly with the massive real-world demands of China's booming AI and industrial sectors. It creates a uniquely accelerated innovation cycle.
They aren't just researching for the sake of getting published in a journal.
No, they're researching to immediately solve critical national-scale technological bottlenecks. The 1-nanometer ferroelectric transistor we're talking about is the ultimate proof of concept for this environment. It signifies the true transition from the more Moore era of shrinking traditional silicon to the beyond Moore era, which relies on entirely new switch devices and novel materials.
That transition from theory to reality is perfectly captured in another personal account I found deeply compelling from our research stack. It involves a doctoral student at Peking University. Her perspective really grounds this massive technological shift in human reality.
The one working on the 2D materials.
Yes. I was reading through her online posts, essentially her diary of this process, and she lived her entire academic life through this intense era of what she called chip anxiety, where seemingly every single news headline announced a new technological restriction or a newly blocked supply chain. But her response wasn't to look for a way around the export controls on silicon manufacturing equipment. She completely ignored traditional silicon. She was buried deep in the world of 2D materials and ferroelectric switching.
Which, from a pure physics standpoint, is the exact right place to be looking if you want to circumvent the limitations we just discussed.
Exactly, and the documentation of her work details these grueling late nights in the lab, endlessly calculating energy consumption metrics, trying desperately to hit a theoretical baseline. And the massive breakthrough for her team wasn't just hitting a speed benchmark, it was hitting that world record low energy consumption of 0.45 FJA.
That number is still staggering to me.
It's wild. The realization was that they could fundamentally merge memory and logic into one single, highly efficient heartbeat. This is the whole compute and memory concept. And when I look at this from a macroeconomic perspective, or even just as an observer of technology, it is clear that for these researchers, this breakthrough isn't just a technical win, it is a profound declaration of intellectual sovereignty. It functions entirely outside the permission of global hegemonies. From my perspective, it's this classic underdog narrative framed by heavy state ambition. They built a new door using completely different material science, and they hold the only key.
And that declaration of intellectual sovereignty is backed by incredibly robust device physics. The specific achievement by Qiu-Cheng Wang and Penglian Mao's team at Peking University, the one published in Science Advances, is revolutionary. Let's deeply analyze the exact technical metrics here, because to an engineer, these numbers are almost unbelievable.
What did they actually do?
First, they scaled the physical gate length down to the ultimate 1-nanometer limit. As we established, silicon starts failing catastrophically below 5 nanometers. To achieve stable electrostatic control at 1 nanometer demonstrates a flawless mastery of atomic engineering.
And the power metrics are even more shocking to me. They achieved an ultra-low operating voltage of 0.6 volts, alongside that energy consumption of 0.45 FJ in a meter. That efficiency doesn't just edge out the competition, it beats current international levels by a full order of magnitude.
It is the most energy-efficient ferroelectric transistor ever reported globally, period.
I really want to deeply unpack that 0.6 volt operating number. To a casual listener, 0.6 volts just sounds like a small battery. But based on the literature regarding ferroelectric materials, hitting that exact sub-1 volt threshold is a massive, historic breakthrough. Ferroelectric materials were stuck in a global scientific deadlock for over 20 years, precisely because of their voltage requirements, right?
Yes, that 2-decade deadlock is crucial context. Ferroelectric materials are theoretically brilliant for computing because they can store data based on their internal polarization state. Think of it as how their internal electrical charges are physically arranged. And crucially, they are non-volatile, meaning they remember that arrangement even when the power is completely turned off.
Like a magnetic hard drive, but operating at the insane speed of solid-state memory.
Exactly. However, the catch for the last 20 years has been what we call the coercive voltage. To flip that polarization to actively write a 1 or a 0 into the material historically required a high voltage, usually somewhere between 1.5 volts and 5 volts. This high coercive voltage meant that while ferroelectrics were fantastic for storing memory, their power consumption absolutely exploded during the active writing process.
Which makes them useless for modern processors.
Entirely incompatible, because the logic chips doing the actual thinking, your CPU or GPU, they operate at very low voltages, typically around 0.7 volts, to conserve energy and prevent melting.
So you have a logic processor operating efficiently at 0.7 volts, but to record any of its calculations into the ferroelectric memory, you suddenly have to spike the system up to 1.5 or 5 volts. You have a massive systemic mismatch.
It is an insurmountable mismatch in a traditional architecture. You cannot build a seamless, efficient system when the two core components require wildly different operating conditions.
Okay, so if the physics of traditional ferroelectric materials demand high voltage to flip the switch, how on earth did the Peking University team get it down to 0.6 volts? Hitting 1 nanometer in a pristine lab is an incredible feat of engineering, but changing the inherent voltage requirements of the material feels like you're cheating the laws of physics. How did they break a 20-year deadlock?
They broke it through a stroke of architectural genius they call the nanogate mechanism. And this is where the beauty of device physics really shines. Instead of trying to alter the chemical composition of the ferroelectric material to somehow lower its intrinsic voltage requirement, which everyone else was failing at, they changed the physical geometry of the electric field applied to it.
They changed the shape of the power, not the material itself.
By aggressively scaling the gate electrode down to that 1 nanometer limit, they harnessed a phenomenon known as the tip-induced electric field concentration effect.
I visualize this kind of like a lightning rod. A flat roof dissipates static charge, but a sharp metal tip concentrates the electric field until it arcs.
That is a phenomenal analogy. Imagine taking broad ambient sunlight and passing it through a magnifying glass to create a tiny, intensely hot focal point. The 1 nanometer nanogate acts exactly like that magnifying glass or your lightning rod for the electric field. It creates a highly localized, intensely magnified electric field region right inside the ferroelectric layer.
So because the gate is only 1 nanometer wide, it acts like a microscopic needlepoint.
Yes. This geometric amplification means the system only needs to supply a very small overall voltage to the gate, just that 0.6 volts. But because that energy is focused entirely through a 1 nanometer tip, the local field strength at the microscopic level is overwhelmingly powerful. It is more than enough to flip the polarization of the material. They achieved high-fidelity data storage without requiring high systemic voltage. It is a brilliant, elegant circumvention of the traditional physical limits.
That is astounding. They didn't need to invent a new power source. They just focused the power they had with atomic precision. But it's really important to note that they couldn't have built this structure on traditional silicon. This entire breakthrough, the very foundation that allows this nanogate to function without destroying the underlying channel, relies entirely on 2D materials.
Yes, completely dependent on it.
The Peking University paper explicitly credits these materials, specifically highlighting single-layer OS2 or molybdenum disulfide. Why is that specific 2D material the absolute cornerstone of this post-Moore roadmap when silicon fails?
2D materials like MOS2 are the perfect, perhaps the only, vehicle capable of supporting this breakthrough. They entirely solve the degradation issues of 3D bulk silicon that we discussed earlier. When you thin down 3D silicon, its surface is left jagged at the atomic level. It is plagued by what we call dangling bonds.
Dangling bonds.
These are atoms at the surface that have unpaired electrons. They act like highly reactive potholes on our electron highway, violently scattering the electrons flowing through the channel and destroying mobility.
But 2D materials don't have these potholes.
No, because of their inherent atomic structure. 2D materials, by their very nature, are atomically flat and perfectly terminated. They consist of a single, highly stable layer of atoms naturally occurring as a flat sheet. Because there are no dangling bonds on their pristine surfaces, there's virtually no surface scattering. You can scale the body thickness of the channel down to a single atomic layer, and the electrons will still flow with incredible high mobility.
Okay, but I want to play devil's advocate here for a second, because the history of semiconductors is littered with miracle materials that worked perfectly in a lab but completely failed in mass production. Hitting 1 nanometer in a pristine university environment is vastly different from commercial viability.
A very fair point.
How do they actually build a chip out of this? How do they stack these distinct layers? The 2D MOS2 channel, the ferroelectric memory layer, the 1 nanometer gate without the defect rate destroying the yield. Usually, when you stack different crystalline materials, the atomic lattices don't match up, causing immense physical stress and defects.
That is the crucial engineering hurdle, and it's where van der Waals integration comes into play. You're absolutely right that in traditional bulk materials, if the atomic lattices don't perfectly align, epitaxial growth creates strain, dislocations, and catastrophic defects. But 2D materials lack these rigid lattice matching constraints. Because their surfaces are perfectly terminated without dangling bonds, they don't form strong covalent bonds with the materials placed on top of them. Instead, they bind through van der Waals forces.
So these are the weak atomic forces, right? The same forces that allow geckos to walk up a pane of glass?
Exactly. It's a physical attraction rather than a harsh chemical bond. This means you can stack a ferroelectric layer directly on top of a single layer MOS2 channel, and they will interface seamlessly without creating any lattice strain or interface defects. This van der Waals integration is the exact physical mechanism that allows the Peking U team to pair a 1 nanometer gate with a ferroelectric memory layer flawlessly.
Incredible.
And regarding your point on mass production, while MOS2 has historically been difficult to grow uniformly at wafer scale, the Chinese semiconductor ecosystem has been pouring massive resources into advanced metal organic chemical vapor deposition, or MOCVD, techniques to solve exactly this yield issue. They are aggressively scaling the lab results into fab realities.
So we have a perfectly flat atomic highway for the electrons and a 1 nanometer magnifying glass to flip the memory switches using almost zero power, all held together seamlessly by van der Waals forces. It is a complete fundamental reimagining of hardware architecture. And honestly, this breakthrough couldn't happen at a more critical time for human infrastructure. The entire world is currently careening toward an absolute energy crisis, driven almost entirely by the explosive growth of artificial intelligence.
The energy trajectory of current AI hardware is entirely unsustainable. It's a looming disaster.
We really need to examine the staggering power demands of modern AI because the numbers are terrifying. Reviewing the recent International Energy Agency report, the scale of the problem is almost too massive to conceptualize. The IEA data shows that in 2024, global data centers consumed 415 terawatt-hours of electricity. To put that in perspective for you listening, that single sector used the equivalent of the entire annual electricity usage of the United Kingdom,
Yes.
And that is just the baseline today. The IEA projects that by 2030, data center power consumption is going to hit 945 terawatt-hours. That is approaching the energy usage of the entire country of Japan, just to power server racks.
And those projections might even be conservative given the rapid deployment of large language models everywhere. Morgan Stanley recently issued a forecast predicting a 47 gigawatt power shortage for U.S. data centers alone in the coming years. We are talking about the equivalent of the total power consumption of 9 cities the size of Miami, simply missing from the grid. The infrastructure physically cannot support it.
And the most frustrating aspect of this crisis, at least from an engineering perspective, is that a massive portion of this energy isn't even being used to do the actual mathematical computation. It is being wasted purely on the logistics of moving data around.
Yes, this is the infamous memory wall.
Right. In the literature surrounding AI hardware, the von Neumann bottleneck is cited as the fundamental flaw in how computers have been built since the 1940s.
Exactly. The von Neumann architecture physically separates the processing unit from the memory unit. The processor sits over here, the memory sits over there.
And to execute any command, the system has to constantly shuttle data back and forth across a physical bridge, the memory bus. I read an analysis stating that in typical AI accelerator chips today, an unbelievable 60 to 90% of the total power consumption is wasted purely on this data transfer.
60 to 90% of the energy is spent just moving the data from the filing cabinet to the desk and back again, rather than actually reading, analyzing, or computing the files. When you are training a modern large language model with trillions of parameters, you're moving mountains of data across that bus billions of times a second. The energy penalty of the interconnect is catastrophic. But it gets even worse when you factor in the voltage mismatch we discussed earlier.
Right, because the logic processors, the GPUs sitting at the desk doing the math, are designed to run at very low voltages, around 0.7 volts, to stay cool and process operations quickly. But the mainstream non-volatile memory, the massive NAND flash filing cabinets holding all the AI weights, needs roughly 5 volts to complete a write operation.
So inside these massive football field-sized AI server farms, the system is constantly having to step the voltage up from 0.7 volts to 5 volts to write the data to memory and then step it back down to process it.
I saw a breakdown showing that this single step-up and step-down process wastes roughly 30% of the electricity in AI servers. It's like using massive industrial high-voltage power lines to charge your smartphone and having to put an incredibly inefficient transformer in the middle that bleeds off a third of the energy just as pure heat. It is an architectural nightmare.
It is deeply inefficient, and it highlights exactly why the compute and memory, or CIM, revolution is necessary, and why the Peking University 1 nanometer ferroelectric transistor is such a paradigm-shifting achievement. By operating natively at an ultra-low 0.6 volts, this new ferroelectric memory perfectly matches the native voltage of the logic chips.
The voltage mismatch is completely eradicated.
Eradicated entirely. You completely eliminate the need for those complex, power-hungry voltage step-up and step-down circuits that are currently burning 30% of a data center's electricity as heat. But the implications go far beyond just voltage matching. Because the ferroelectric transistor has the unique physical property of being able to both process logic operations and store non-volatile data simultaneously, memory and computation can now happen in the exact same physical location.
The desk and the filing cabinet become the exact same thing.
You don't have to move the data across the bridge anymore. You compute the data exactly where it rests in the array. Going back to your transformer analogy, the Peking U team didn't just build a slightly more efficient transformer. They perfectly matched the native voltage of the charger to the native voltage of the phone. And by integrating the logic into the memory cell itself, they completely eliminated the 30% waste and the 60 to 90% data shuttling waste simultaneously.
That elimination of waste isn't just a win for the cooling bills of giant server farms, though. It fundamentally changes where the computation can physically happen. If the energy consumption drops by an order of magnitude, you don't need to situate a sprawling data center next to a dedicated nuclear power plant or hydroelectric dam just to run a powerful AI model. You can bring massive, powerful local AI capabilities directly to edge devices.
That is the true strategic horizon. We are talking about highly sophisticated, parameter-dense AI running natively on your smartphone, inside autonomous robotics, in wearable health monitors, and throughout the distributed Internet of Things. And it does this completely autonomously without relying on a constant, latency-heavy, privacy-compromising connection to a centralized cloud server. You get complete data privacy, instantaneous zero-latency response times, and massive computational capability right in the palm of your hand, all powered by a deeply efficient 1 nanometer ferroelectric switch.
Looking at the local industry sentiment right now, there is a fascinating pivot happening that perfectly illustrates this shifting horizon. I want you to imagine a small startup founder I was tracking in Shenzhen. Shenzhen has long been known as the hardware capital of the world, famous for incredibly rapid iterations and scaling of existing technologies. But this specific founder is trying to build a business fundamentally based on neuromorphic architectures.
Chips designed to mimic the human brain.
Exactly. Chips designed from the ground up to mimic the synaptic structure and parallel processing of the brain. And the accounts note that he recently executed a complete overhaul of his business strategy and investor pitches.
And what triggered that pivot?
He recognized the physical ceiling of the old paradigm. He completely stopped pitching his company to venture capitalists as a low-cost alternative to Western AI chips. He stopped trying to be a cheaper copy of an NVIDIA GPU. Instead, he started pitching his company as a native inhabitant of a completely new parallel ecosystem. He realized that this emerging ecosystem isn't built on the old, restricted pillars of Dutch optical lithography machines or American software monopolies like CAD. It is being built from the atomic level up on the unique, unrestricted physics of Chinese-developed ferroelectrics and 2D materials.
He recognized that the foundation had fundamentally shifted beneath the industry.
Exactly. He talks passionately about a future where AI isn't confined to those massive, power-hungry data centers, but thrives in tiny, hyper-efficient edge devices utilizing native compute and memory. He's building spiking neural networks that function natively on these new chips. When I analyze this proactive pivot, it reveals a profound psychological shift in the tech sector over there. He has moved his entire mental framework from a defensive posture of how do we survive the export controls and build a cheaper copy using older machines, to an incredibly aggressive, forward-looking posture of how do we unequivocally define the post-Moore era. They are building a completely new house because they were evicted from the old one, and they are ensuring, through basic physics, that the new foundation is something no one else owns the patent to. They are actively securing their own technological destiny.
That Shenzhen founder's strategic pivot is a perfect microcosm of China's broader macroeconomic strategy. China's proactive approach to constructing the post-Moore semiconductor ecosystem is highly systematic and heavily resourced. They recognize fundamentally that this isn't just about commercializing one successful 1-nanometer chip from a Peking University lab. This represents a definitive strategic fork in the history of human computing. By focusing intensely on foundational physics breakthroughs, they are establishing a unique, unassailable leadership role.
And it's not just ferroelectrics. The research shows they're constructing a deeply diverse technological stack to support this new ecosystem.
It is a multi-pronged, heavily integrated approach. We've deeply discussed 2D materials like MOS2 and ferroelectric nanogates. But the Chinese state research apparatus is also deeply investing in memristors. Memristors are fundamental circuit components that can remember their past electrical states, making them the perfect physical analog for mimicking biological synapses in neuromorphic computing. They are simultaneously advancing photonic computing, which utilizes photons instead of electrons to process data, theoretically allowing computation at the speed of light with near-zero heat generation.
So they're building optical chips for interconnects while building ferroelectric chips for logic and memory.
Yes, and they're unifying these disparate technologies through a mastery of heterogeneous 3D integration. This is the advanced packaging ability to seamlessly stack these different novel logic layers, memory arrays, and photonic sensors vertically. This vertical integration drastically reduces the physical distance data has to travel, further eliminating latency and maximizing three-dimensional space efficiency.
It's an entire self-sustaining arsenal of next-generation technologies. And what strikes me, reviewing all these developments, is that post-Moore innovation operates as a strict winner-take-all scenario. If an industry is just making incremental geometric improvements to traditional bulk silicon, the major players are essentially just sharing the market. You have a 3-nanometer chip, I have a 3-nanometer chip, and we compete on price. But if someone fundamentally changes the underlying physics of the device, the entire global architecture resets. When a country hits a foundational physics breakthrough first, like mastering stable 1-nanometer compute and memory on 2D materials, every single layer of the technology stack built above it is forced to reorient around that discovery.
It creates a massive gravitational pull on the entire industry standard.
The packaging engineers globally have to design entirely new ways to manage the thermals and stacking of 2D materials. The systems architects have to design completely novel motherboards to utilize compute and memory arrays instead of separate RAM and CPUs. The AI software developers and algorithm designers have to throw out decades of code and write entirely new frameworks to take advantage of the fact that memory and logic are now physically merged. The country that successfully defines the physics of the bottom layer dictates the operational rules for everyone else stacked on top.
That is the ultimate strategic leverage. This transition to a materials-driven breakthrough fundamentally shifts the global balance of power. It moves leverage away from manufacturing bottlenecks, away from who controls the export of a handful of EUV lithography machines, and heavily favors the nations with the deepest scientific talent and the most robust basic research capabilities. When you frame this within China's current innovation environment, the advantage becomes clear. They have cultivated a massive, highly educated pool of STEM talent, supported by a government that provides sustained, unwavering funding for deep, foundational basic research. This research isn't subject to the short-term whims of quarterly earnings reports or venture capital hype cycles.
It is patient capital applied to fundamental physics.
And this highly effective fusion of patient, deep, basic research with the immediate, insatiable industrial demand of China's domestic AI sector creates a brilliant, diverse path forward for human technology as a whole. It thoroughly shatters a long-held Western stereotype that fundamental, paradigm-shifting innovation can only originate from places like Silicon Valley. By fearlessly exploring these diverse, highly complex technological paths, mastering 2D van der Waals integration, redefining ferroelectric physics, scaling compute and memory, China has provided the global semiconductor industry with desperately needed new architectural options. This is critically important today, as global AI energy consumption morphs from a logistical headache into an existential threat to our climate goals.
It really is a profound shift in perspective, moving from a narrative of restriction to a narrative of reinvention. Synthesizing all the research, data points, and accounts we've explored today, a clear picture emerges. The highest form of technological decoupling isn't just about throwing billions of dollars at building your own domestic supply chain for yesterday's technology. It is about executing innovations so profound, so fundamentally different, that it renders the existing geopolitical restrictions completely irrelevant. China has clearly recognized that there is no strategic value in simply trying to match legacy giants node for node in a legacy race where the rules were written against them. Instead, they are boldly writing an entirely new technological roadmap, and they are basing it on the immutable universal laws of physics. While the rest of the world is betting their economic and geopolitical strategies on aggressively controlling the legacy factories of today, the true victory belongs to whoever masters the physics of tomorrow. And this 1 nanometer device proves that tomorrow has already arrived.